Welcome back, everyone. And now we get to some mind-puzzling blogging aspects in correlation clustering. So now we leave this area of the taxonomies and of the different aspects and get to some special cases in this topic of arbitrary-oriented subspace clustering. So under the provocative title of Computers Act in a Binary World, Correlation Clustering 2, consider the following case, which is motivated by this line. By all of the PCA-based correlation clustering algorithms like SSCC, ORCLUS, even 4C, COPAC, and so on, the distinction between cluster and correlation subspace is done by determining in these two categories of weak and strong eigenvectors. So a strong eigenvector is, for instance, a direction here with a large variance, and a weak one is, for instance, this here with C equals 3. So this variance, for instance, so this ABC, these indicate different variances. And here you see these ellipsoids that cover the subspace that we are looking at. So this is from a PCA which detects this particular ellipsoid. This is what you see here with different parameters. But we challenge and ask, is this distinction between weak and strong eigenvectors actually like a good idea? Does it make sense? Is it binary? Can we say this is strictly strong, this is strictly weak? And for this, let us consider the first case. So the explained variance of a threshold alpha is here like 0.6. We just say this like 0.6. So we as a fantasized or arbitrary chosen, we say here we have the explained variance threshold alpha, so not A, but alpha, we want to have like 60% of the variance being explained by using only this or with this or this. So in general, we want to have a subspace which covers 60% of the explained variance. So the principal component A, this one here, already satisfies this threshold. How that? A has a value of 10. A plus B, this red one, plus C, so 10 plus 3 plus 3 is 16. 10 divided by 16 is 0.625, and 0.625 is greater than alpha, which means A, so this one direction that we have here, is the strong eigenvector, and B and C, these two ones, are weak eigenvectors. Okay. Now, consider that we increase the variance in the direction of B from 3 to 5. Then the principal component A is no more satisfying this threshold. Why that? Because eigenvalue of A is like 10. 10 divided by 10 plus 5. Before it was 3, now B is 5. Plus 5 plus 3 from C is 0.556, and this is smaller than alpha that we demand. So if we add now the principal component B to the strong eigenvector, so if we say the eigenvalue of A plus the eigenvalue of B, so sorry, there's an error here in the slide that I will fix. There we have 10 plus 5 is 15 divided by 10 plus 5 plus 3, and this is 0.833, which is much bigger than actually demanded. So here we see already a case, if we only take like the one principal component of the direction of A with the eigenvalue of 10, we no longer meet, or closely with 0.05, no longer meet this, and here we are way above. So from the second case, we get the explained variance threshold alpha 0.6 is only satisfied if we also add this second principal component, meaning if we extend from a one-dimensional subspace to a two-dimensional subspace. And adding B to the set of the strong eigenvectors. But then we get way more explained variance than we actually demanded. However, the fun fact here is adding only principal component despite not being the second strong vector. So adding adding the principal component of A with, like, for instance, the principal component of C we will still not have the sufficient amount of variance that we need here. And I see that I kind of missed the point here. So that was complete garbage what I spoke now. So let me check this. Adding only principal component, despite not being the second strongest PC principal component, yields together with PC of A enough explained variance. Yeah, so adding only like this one here, like the 10 with this 5 one here yields then indeed enough explained variance. So the preliminary conclusion that we have here, the explained variance thresholds, like this alpha 0.6, they are highly depending on the given data set. And this is indeed not trivial or suitable to state what a strong or a weak subspace is, because here we have 0.556 and say, nah, this direction is not enough. But maybe it is because we are quite unflexible with this threshold alpha 0.6 here. So one research question that we have at this point, is there a way to compute or derive from the data suitable explained variance thresholds individually per cluster? Because in subspace correlation clustering or also in other algorithms, this explained variance threshold, 0.6 per instance, or 0.8, some are even hard-coded. As far as I recap, I think SSCC subspace correlation clustering has hard-coded, it says 0.8, so 80% of explained variance, that's exactly it. If it's below, then it's not good enough. But this is quite inflexible, and it is a global value for all clusters and not for single clusters individually. So a research question that I also address to you as a dear audience, if you have a cool idea, is there a way to compute or derive from the data suitable explained variance thresholds individually per cluster, which is not so static, holding to one fixed constant? And with these words, I conclude that section, and yeah, stay tuned for the last video. Take care.